to peg C, right there. So that's it there. Let me play the game. I can stop sharing right there. And let's do it with one disk. That will be the initial condition. That will be the initial condition of this recursion. So if I were to have one disk, there I have one disk. In order to go from peg A to peg C, it requires me one move. T of 1 is 1. T of 1 is 1 right there. It took me only one move right there. So T of 1 is 1. So back to our notes. Let me share with you. There. T of 1. It's equal to 1. That's the initial condition. Let me play with two disks right there. I'm going to put two disks. I'll share with, let me see. Let me stop sharing. Two disks. Okay, I'm going to do this. My first move, 1. My second move, 2. My third move, 3. 4. And it took 5 moves, but let me do it. So it should be less than 5 moves. Let me see. There. I'll do it again. 1, 2, and 3. 3 moves. I was playing a different game. 3 moves I need. Okay, with that, let me do it again. I was doing it with adjacency. So let me do it right away, right there. So you start like that. All the moves to move two disks from peg A to peg C. 1, liberate this one. 2, and 3. 3 moves. 3 moves to move two disks from peg A to peg C. So that's it. That here I'm playing, here I'm doing the work on the side right here. So that's the initial condition. Let me share with you. I have the initial condition. I'm clear with that. Let me see there. There. That's the initial condition. But then here, T of 2. I ended up with the 3 right there. So I'm going to play with 3 disks. I'm playing with the game in order to come up with a recursion. I think I need to think recursively in a minute, but I'm getting used to the game. And then I will think recursively. Back to the game. Right there. So I'm going to play with 3 disks. And then I'll think of what's going on with the game recursively. I haven't thought recursively yet. So here I go. 1, 2, 3, 4, 5, 6, and 7. It took me 7 moves to move 3 disks. Right there. I have a Tower of Hanoi in my phone, and every time I'm stuck in Newark, I play Towers of Hanoi at the Newark airport. Right there. Not at LaGuardia because they have a new airport and it's nice to explore. But I don't care exploring Newark. Right. I'm sorry. I don't care exploring Newark. But let me go. Let me go right away. Do it again. 1, 2, 3. That's like a T2. I just did a T2. I start thinking recursively. A T2 put me here to liberate the last disk. And then I'm going to do another T2 to put these 2 up here, right there. So, but let me do it again. Yeah, that's the T2. Here it comes. So I started thinking recursively. I have 3, but I'm thinking of T2. Here comes the T2. 1, 2, 3. That's the movement of a T2 to some other peg. And then comes the 4, the 5, the 6, and the 7. That was another T2. So I do whatever I had in terms of the disc before. So here is the algorithm. The algorithm is, I have a T3, but I'm going to think T2. And I'm going to move all of them right here. And that took me 3 moves. Then an extra move to move the last disc. And then I'm going to think T2 again to bring it right there. So there is the algorithm recursively right there. So then I'll try with T3 again. I'll try with T4. But let me come right here. So I thought recursively, I share with you once right there. There. So let me see. There. And then that was T2. But to play with T3, I ended up with a 7. And then I asked myself, I want to use T2. The previous one, TK minus 1. So to compute this, in order to use T2, this is what I ended up with. T3, I computed a T2 to liberate the last disk. And then I moved that last disk, which was the 3rd disk. And that was 1 move. Plus, I performed T2 again, right there. So that's the minimal number of moves, is because I need to liberate that last disk. So let me play T4. And of course, that gave me 3 plus 1 plus 3, which is the 7. Right there. But let's play with T4. The claim. How much will be T4 if I'm going to think T3? So how many moves T4 should have? If I'm thinking in terms of T3.
15.
15. Yes. Because I better do a T3 to liberate the last disk, the 4th disk, and then move that 4th disk, and then do a T3 again. And ultimately that will be 2 times T3 plus 1 right there. So we'll simulate it right away. First, we'll do them all right there. So I'll grab 4 disks at once. Right there. I'll share with you. There. I'll put an extra disk. So it's right there. Let's do it first, let's say, non-stop. I'm going to perform a T3, and I'm going to leave all the disks right here. So it's going to be a 1, 2, 3, 4, 5, 6, and 7. That was a T3 in order to liberate that last disk right there. So, and now that's the 1 for the last disk. So that's the 7 plus the 1. And now another T3. So it's divide and conquer, this type of algorithm. So I'll do the other T3. And that will be 1, 2, 3, 4, 5, 6, and 7 right there. So that's it. And now we can do it. That was 7 plus 1 plus 7. But now that's a T3, 7. That's the 8th. And that's the 7 again right there. So that's it. We have it right there. So coming here, and again, let me share with you. The minimum number of moves is because I need to liberate that last one right there. Perfect. So let me see. I'll go and share with you at once. And go right away to here. So we have a conjecture. Well, that's it. The recursion is tk, it's equal to 2 tk minus 1 plus 1. And the initial conditions are, well, is one condition right there. T of 1 equals 1 right there. And that is the recursion right there. Happiness with that. We have the recursion. Now you know what we want. After the recursion, we want a closed form. We want a formula right there that the elements of this recursion will satisfy. So find an explicit formula. So stop. The first part is done. This is running through time. And now, of course, I need to put here k is T of 1 is 1, and then that's tk, and then here I will put for k greater than equal to 2. Right there. Let me write the k like that. Perfect. That's it. Let me circle that. So that's our recursion. Now, in order to try to find the explicit formula, let's get some numbers. We are going to do backtrack right there. We're going to do plug and chug. But let's get some numbers of the sequence. This is a sequence, a recursive sequence. One number is 1. The next one was 3. The next one was 7. The next one is going to be a 2 times 7 plus 1 is the 15. The next one is
31.
what is it? What is it? Let me put the volume.
31.
I'll check out once. Yeah. 31? 31?
Yes.
31. One more.
62.
62?
63, sorry.
63, 63. Perfect. And so on. Right there. So we can do plug and chug. We will do plug and chug. But you can guess. You can guess what could that potential with this sequence. What this sequence potentially could be. So one way is just guess it from the pattern. And don't do plug and chug. Just guess it by the pattern and then do induction to see if it works. Could you guess it by the pattern? Oh, let me check the chat. Oh, that's the next one, but the pattern of the explicit formula. Okay, the 7 is very close to the 8, and the 8 is the 2 to the third power. The 15 is very close to the 16, and the 16 is a 2 to the fourth power. The 31 is, my voice is changing out of emotions. The 31 is very close to the 32, and that's a 2 to the fifth. So what should the formula be by a guess?
Is it 2 to the n minus 1?
2 to the n minus 1. Yeah, Tn. And this is for n greater than or equal to 1. Right there. But in many situations, I would have not ended up with a guess right there. So then we can do it. We can get this same answer by plug and chug. We will try to get this answer by plug and chug right there. So perfect. Let's go and try to get this answer by plug and chug. So that was a guess. Right there. Right there. So plug and chug is also a guess, but let's go and do it. Plug and chug. Let me take out the ruler. Plug and chug. Right there. And we do it both ways. Forward and backward. Right there. So, perfect. Let's go for the forward. So, T of 1 is 1. Right there. T of 2 is 1 plus 2 T of 1. But since T of 1 was equal to 1, this is 1 plus 2 right there, because T of 1 is 1. So I didn't have to do that much chugging. I only did plugging. Let's do T of 3. T of 3 is 1 plus 2 times T of 2. But I'm going to do the plugging. I'm going to plug in this for T of 1 plus 2 for T of 2. So T of 3 is 1 plus 2 plus 1 plus 2, and ends up being 1 plus 2 plus 2 squared right there. So perfect. Now I'll play a little bit backwards right there. So backwards is T of K. It's equal to 1 plus 2 T of K minus 1. But T of K minus 1 see, I have too many windows there. T of K minus 1 here. T of K is 1 plus 2. And then I'll put the parentheses. and t of k minus 1 is 1 plus 2 t of k minus 2. Right there. So this is something that I didn't do in any of my classes before this one. Right there. I didn't play with this in pre-calculus, in calculus 1, in calculus 2, in trig, nothing. This is a new technique. So then it made me mad. I had to practice it. Right there. And so I just did the plug on the backward, and then I need to do some chugging right there. So perfect. Let me do some chugging. 1 plus 2 plus 2 square t of k minus 2. Right there. So that was a little bit of backwards. Right there. Let me do a little bit more backwards, and then I'll go back to the other method. We're doing both at the same time to be able to get the same answer. And we know the answer is 2 to the n minus 1. And then here, tk minus 2 is 1 plus 2 tk minus 3. Right there. So for a while, when I learned this, it makes sense when the professor, when she was doing it, it makes sense. But then when I had to do it for homework, I will get stuck right there. So that happens. That happens with something new. Then, of course, I just did the plugging. I replaced the t of k minus 2 by 1 plus 2 t of k minus 3. And now I need to do some chugging. To square plus 2 cube t of k minus 3. Can you see that we are ending up with powers of 2? We have power of 2 in this series that we're creating, this finite series. So let me go and get a T4. I'll get a T4 right here, and then we're ready to try to come up with a formula. So T4 is the 1 plus 2 T3. But T3, it's all of this. It's 1 plus 2 squared. So that's it. T4 is 1 plus 2, open parenthesis, 1 plus 2 squared. That was the plug. And now we're going to do some chugging. Chugging here is only distributive. I will distribute the 2. There, right there. So I can see some sort of a pattern right here. The 4 gives me a 3. The 3 gives me a 2. And the 2 gives me a 2 raised to the first power. The 2 gives me 1 plus 2 raised to the first power. And the 1 gives me 1 plus 2 raised to the, well, that one is the initial condition right there. I was gonna put, no, there, nothing with that one. That's the initial condition. I leave it like that. That's fixed. Right there. So perfect. There is one less. So here, I can make a claim. So TK is 1 plus 2 plus 2 squared plus 2 cubed plus 2 raised to the k minus 1 right there. And I'll highlight. That's the guess from plug and chug forward. The guess from plug and chug forward. Let's play right now with the plug and chug backwards. So the reasoning on this one. What's going to happen? This k, this entire number, let me highlight it. All of this, k minus 3 and so on, is going to go down. It's going to keep going down all the way to 1. So the k will start increasing. There, k minus 3, k minus 4. All of these will keep decreasing all the way to 1. All the way to 1. So how can I possibly get all the way to 1? Well, I can get all the way to 1 where I get to that moment right there. That moment will get me all the way to 1. K minus 1. Because it's gonna be a k minus 3, k minus 4, k minus 5. But it's not gonna go forever. I mean, it's gonna go all the way to 1. That is 1. K minus 1. Now, the 3 that we see right here is gonna keep increasing. It's gonna be 3, 4, 5, 6, but all the way to a k minus 1. Right there. Can you see there is the analysis on the backward. So that's it. So ultimately we'll end up with something like this. TK 1 plus 2 plus 2 squared plus 2 cubed all the way to a 2 raised to the k minus 1 times t of 1 times t of 1. And that the t of 1 is 1. Right there. So you end up with the TK 1 plus 2 plus 2 squared plus 2 cubed plus all the way to 2 raised to the k minus 1. Right there. So let me highlight that one. That was done by backtrack. And the other one was done by forward. And they both check. Can you see how those two check? Many times one could potentially fail, that is not going to give you any information, and you continue with the other one. And usually the backward is better, right there, reaching more complicated recursions. Happiness with that. So I was doing double the work. I didn't have to, but there is practice with both, right there. So that's it. We have a formula. we have a formula that says 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3 plus all the way to 2 to the k is equal to 2 to the k plus 1 minus 1 over 2 minus 1. Right there. That's the formula that we have from the textbook. So we need to bring that formula to our notes. And now we need to massage. We're not going all the way to k. We're going all the way to k minus 1. So it will be one less right there. So perfect. TK. Let me change the color. TK is 2 to the 0 plus 2 plus 2 squared plus all the way to 2 raised to the k minus 1, and that is equal to 2 raised to the k minus 1 over 2 minus 1, which is 1 right there. So we have it. We have it. So now our guess is Tn equal 2 to the n minus 1. Right there. So 64, we need induction. We need to do induction. But when this came out, when the towers of Hanoi came out right there in the 30s, in the 1930s, right there, by the number theories, by the mathematician, and they sold the game, you will get a prize. You will get a prize of $40,000 if you finish the game. If you finish the game, it has 64 discs. So let's compute T64. T64 is 2 raised to the 64 minus 1. Right there. The legend said also that when the monks finish moving all the discs to the last peg, the world will crumble. The world will come to an end right there in the game. Look, 2 raised to the 64 minus 1, at least during those times. I'm not sure nowadays because I'm not in astronomy, but it is close to the age of the universe. It's close to the age of the universe right there that they were estimating at least 10 years ago right there. That changes, so I'm not sure what was the age of the universe, but check that number and it should be close to how I'm going to check it with ChatGPT. Is 2 to the 64 minus 1 near the age of the universe? That right there. So that's why nobody got the prize. The French were tricky right there. A little trickeration by the French. Nobody won the prize because, I mean, you cannot finish the game with 64 discs right there. They were not asking for the solution, but they were asking for finish it. You can't. Right there. Perfect. Okay, so we're missing induction. So induction is show the elements of the recursion. We started with the recursion. Elements of the recursion. Satisfy the formula 2 to the n minus 1 right there. the explicit formula right there. So that's induction. That's induction right there. And of course, we know the recursion. The recursion is tk equals to 2tk minus 1 plus 1 right there. So let me put it right here. Elements of the recursion. I'll put it right here. What do we mean by element of the recursion? I put it here tiny. Is the tk equal to 2 tk minus 1 plus 1 with the initial condition t of 1 equals 1. So I put the recursion right there. So the recursion comes first. So we have to do induction. It's not a plugin. It's induction. So perfect. Let me see. I'll make the induction. I'll make this problem. This last thing. Let me see. I'll make it an immediate homework. Just showing this. Okay, with that right there, doing the induction part. So at the end of the class, I will post it as an immediate homework. And let me do another recursion problem. Let me do another recursion problem. So let me see. I'm gonna put here U induction. So induction, I'm gonna put U 2 and for South America and El Salvador, both, meaning Argentina, Uruguay, and El Salvador, right there, both, right there. Happiness with that, perfect. There, and Costa Rica too, yeah, perfect. There. So let me. Yeah. I mean Costa Rica too. I mean Costa Rica also they can use both right there. Okay, so perfect. Let me go right away to do another problem right there. Let me see a super cool problem from the textbook. Perfect. Here, compound interest. That's a recursion. Compound interest is a recursion right there. So perfect. So the amount, well, I'm going to have some initial amount. 8 naught. Let's say is $100,000 right there. So I have some initial amount in terms of money right there, $100,000. So let's start thinking recursive. Well, let's start coming up with the recursion. So in the first year, I'm still going to have that money plus, let's say the interest is 4%. And then I'm going to apply the 4% to that initial amount right there. And that will be on the first year. It will be the $100,000. And then take that 4% and multiply by the $100,000. And that will be year 1. And then I'm going to go to year 2. And this feels like the Towers of Hanoi. Year 2. Well, I'm going to have the money on year 1 plus right there. And then I'm going to multiply that by 4%. And that is going to be year 1 right there. Can you see? But then I want to write it in terms of year 0 right there. So in terms of year 0, year 2, well, I will continue this. So I'll get the recursion. Year 3 is going to be year 2 plus 0.04 of that year 2. So I have a recursion. The recursion is year K is going to be the year K minus 1 plus the 4% interest, annual interest applied to that earlier year. And then 8 of 0 was $100,000. Can you see right there? That is the recursion. That is the way that compound interest work right there. And I'm looking at example 5.6.7. .6.7 right there. So that's it. We have the recursion. You know what we want? We want also the explicit formula. So we have the recursion right here. So we want to play plug and chug to end up with the a formula. We would love to end up with a formula. Happiness. Perfect. So that's it. Now plug and chug. But that is the perfect. So they're compounding once a year. This is annual interest. So let's go and find an explicit formula right there. So let's start with right there, forward. And backward, plug and chug. Right there. So forward, A of 0. And of course, I need to say here, and this is for, sorry, I need to put the, and this is K greater than equal to 1. Of course. K in the naturals. Right there. So let me circle all of that. So, perfect. A of 0 is the $100,000 that I can keep as A of 0 right there. But 8 of 1 is 8 of 0 plus the 4%, 8 of 0 right there. 8 of 2 is the 8 of 1 plus the 0.04, 8 of 1. But remember that 8 of 1, it's 8 of 0 plus 0.04, 8 of 0 plus 0.04 and 8 of 1 again. I'm plugging both. I'm gonna need more space. Right there. 0.04 and then here 8 of 1 is 8 of 0 plus 0.04, 8 of 0. And then let me put the fence right here, almost backwards. No space for backwards right there. So perfect. Let's make So here I have an A of 0 that I will factor right there. And I can see a 1 plus 0.04. And then I'm going to see right here a plus 0.04 plus 0.04 squared 8 of 0. Right there. And then factor that initial, the $100,000 from both. And I'm going to see a 1 plus 2 times 0.04. Let me erase that. 1 plus 2 times 0.04. Plus 0.04 square and close. Right there. And then I'm going to try to factor that right there. Look, it's the first one plus 2 times the second one plus the second one square. So look at what it looks like. It looks like 1 plus 2x plus x squared. Right there. And what is 1 plus 2x plus x squared?
1 plus 1 plus x
1 plus
squared.
grass. Thank you, we. Yeah, 1 plus x squared. So this one will be there. Let me see. It will be equal to A naught, the $100,000. 1 plus 0.04 square. And that is A2. Right there. So look at the pattern. Right there. So I can make a conjecture. The conjecture will be that A3 is going to be A naught 1 plus 0.04 raised to the 3. Right there. And I can try it. A3 is going to be that initial amount of money, the $100,000. 1 plus 0.04 raised to the 3. Right there. And ultimately we'll make it. That's my conjecture. So let's try. So I decided to punt on backward because I don't have enough space for backward. So I'll do it only forward right there. So let me check it. So let's check A3. A3 is equal to A2, whatever money I had already to year 2, plus give me the interest, the annual interest on that money that was at the end of year 2, right there. And now we're going to plug in right there what was year 2. So A3 is, for year 2, we had A naught 1 plus 0.04 raised to the second power plus 0.04 0.04 A naught, meaning 0.04 A naught 1 plus 0.04 raised to the second power. So I need to see if I get the coefficients of the cube. The coefficients of the cube are going to be 1, 3, 3, 1. I'm dealing with the Pascal triangle right here. 1, 1, 1, 2, 1, 1, 3, 3, 1, and so on. So here, I can factor the A naught. And as soon as I factor the A naught, oh, I can factor the A naught and the 1 plus 0.04 squared. And what are the leftovers? As soon as I factor that, I will have a 1 plus 0.04. Can you see how I factor? I factor that term, the entire thing, the A naught times 1 plus 0.04 squared. It's on both. It's here and it's here. So I can factor that. And as soon as I factor that, you can see that we get the conjecture. Is an A naught 1 plus 0.04 cube right there. 1 plus 0.04 cube. So perfect. So now we have a guess right there for a formula. The guess for a formula will be AK is A naught 1 plus 0.04 raised to the kth right there. So let me write it down. And of course, the 0.04 is the I, is the interest. So in general, right there, it will be AK will be A naught 1 plus I raised to the kth right there. That's the formula for the simple interest there, compounded once a year right there. So of course I need to check this by induction. But this is the explicit formula. I'll check that by induction. That's the explicit formula. And I need to check it by induction, but that's the potential explicit formula. And the recursion is AK. It's equal to the AK minus 1 plus the I, the 0.04, times AK minus 1. Right there. Oh, let's write it better. The recursion is AK 1 plus I A of K minus 1. Right there. Comma. And the initial condition, it was A of 0 equals the initial amount on that account. That it was the $100,000 right there. So here is the recursion. Let me see. I put it in full splendor right here. A0 is whatever you deposit right there. And then of course I need to say that K, this is for K greater than equal to 1 right there. And of course K in the naturals. So we have the recursion. And of course, I is 0.04 for this problem. In this example, the interest rate. is 0.04. So we have everything, the recursion, and right under it, the explicit formula, the time traveler. It can go anywhere. AN, it's equal to A naught 1 plus I raised to the N. So we have both right there, recursion and explicit. And of course, yeah, and N, of course, N starts at 0. I can say N in the naturals. Happiness with that. We haven't done induction right there. We need to do induction to show that the explicit is being satisfied by the recursion, that the element of the recursion. Happiness with that. So this is very useful. Money in the bank is recursive. And of course, the formulas could get a little bit more complicated if you are compound more. If you are compound more than once a year. They are not that much more difficult, but they are slightly more exciting, and they put that on. Okay, let me put it right here. Adjust. So suppose yeah, it's on the next example. Let me see. There. Example 5 right here. I'll put right here. Example 5.6.8. Compound more than once a year. Compound several times a year. Compounding several times. Several times per year right there. Okay, let me see. I need to do induction on this. So this is, I didn't cover this. Several times a year. I didn't cover that right there. There. Let's go and do induction. Let's go and do induction. There. So show that the elements of the recursion satisfy A naught one plus I raised to the N. Okay with that? Keep in mind that if you're taking a class in finance, they make the A naught equal to 1 because you want to know the effect on $1. And then you multiply that by the money that you have right there. So they do all the movement on 1 unit, on $1 right there. So the A naught will be 1, and then you multiply by whatever money you need right there. Okay with that? Okay. But perfect. Let's go and do this right there. So solution right there. So the solution will be let Pn be the predicate elements of the recursion. Of the recursion satisfies the explicit formula. Elements of the recursive definition of the recursion satisfy the formula A naught 1 plus I raised to the n. That's AN right there. Put the quotes. So base step. Show P of 0 holds. There. So go to the recursion. If I plug in 0 on the recursion, well, no plugins. A of 0 is 100,000 right there. So in the recursion, so the initial condition of the recursion, the A of 0 is the principal right there. So the A of 0 is the principal, and the principal is 100,000 right there. So the initial condition, A of 0 is the 100,000. And the formula, the explicit formula, A of 0, 1 plus I raised to the 0 is A of 0 right there. So it's true, they check. Hence, thus, P of 0 holds. Perfect. Next, inductive step. Show P of K implies P of K plus 1 is true. For all K greater than equal to 0. Right there. In the naturals. For all K in the naturals. Right there. So I'll take a look at the recursion up here. And then we're going to increase the recursion. Where are your recursion? Right here is the recursion. So I'm going to increase on the consider. I'm going to increase. There I'm going to put a K plus 1. And there I'm going to put a K. Right there. To go to the P of K plus 1. Right there. So perfect. So assume PK, comma. That means right there that the recursion, which is the AK, it's equal to the 1 plus I raised to the K times A naught, satisfies the formula, which is A naught 1 plus I raised I'm sorry, there I put the formula. The recursion, that is raised to the k, the recursion, right? AK, it's a to the k minus 1 plus I k minus 1, right there. That satisfies that. I could have written it like this too. 1 plus I raised of k minus 1 AK. Now, consider A of k plus 1. It's equal to A of k times 1 plus I A of k, right there. But we are assuming this for A of k. So plug in to get, and then replace. So A of k plus 1, it's equal to 1 plus I. And I will put the formula. The formula is A naught 1 plus I raised to the k, right there. So there, I'm assuming the pk. I'm replacing this. I was replacing AK by the explicit formula. That's assuming pk. And then I add the exponents. This becomes A naught 1 plus I raised to the k plus 1 as desired. That's it. The power went by 1 right there. That's the formula that I wanted. So hence, P of k implies P of k plus 1. The formula continues for all k in the naturals. Thus, by PMI, Pn is true for all n in the naturals. Right there. So it doesn't look like I've done much because you continue with that power. We continue with that power right there. And the math was this. Just add up the exponents right there. But that's it. That is the compound interest as a recursion and the compound interest by an explicit formula right there. So perfect. We're using our tools, which are sophisticated tools, on a formula that potentially you knew before. The explicit formula. You knew the explicit formula. Maybe you knew the explicit formula before for simple interest. But we look at it as a recursion. And then we use induction to prove that they match. Okay with that? Okay. So I must give you super freedom and create that immediate right away. I'm sorry I kept talking. So I must give you super ultra freedom. Any questions? Any questions?
I was wondering if our test was still going to be on the 6th.
Oh, let me see. Right there. Let me run to our syllabus at once. Let me see. I'm sharing with you. There. And then of course, let me click there. And then let me click on us. And I'll run to the syllabus. Thank you for the question, Milani. Let me see. There. We're on week 13. Yes, yes. Our test 3 is on the 6, right there. Ciao, ciao,
Thank you. See you on Thursday.
ciao, Brendan. Ciao, ciao, Hope.